Alrighty guys, we're going to go ahead and get started with these Introduction to Kinematic notes. So first thing on our agenda is to figure out what is kinematics. Well, kinematics is just the study of motion. So kinematics is going to help us figure out how to describe certain types of motion and make predictions based on our information on what type of motion should take place. And you'll see what I mean when we have a word type problem. But basically, kinematics is just a nice way of us to use math and physics to make educated guesses on how objects are going to move. We have three equations right here below. These three equations, we call them in this class big dog, little pup, and shaggy cat. There's really no specific reason for that other than the fact that this one over here, big dog, is kind of like our go-to equation. It's the one that we'll always try to use first when we're missing two variables because usually it can get the job done pretty well. The next one's little pup, and the reason we call it little pup mostly is just the fact that it's a little tiny equation and it just looks so cute, right? Look at this, only 4 little variables, adorable. And then our last equation is shaggy cat, and we call it shaggy cat because it's kind of terrifying. We got some squareds here, we got some parentheses, all right, so we got to remember our order of operations when we're trying to do this. And yeah, it's just it's a little bit more difficult to use than the other equations. Next up, what we want to do is talk about our symbols, because as you guys can see, we have symbols inside each of these equations. So the first symbol I want to mention is df, and df is going to stand for our final distance. And since it's a distance, it's going to be measured in meters. Our next symbol is going to be DO, and that's going to stand for original or initial distance. Again, it's a distance, so it's measured in meters. Next, we have VF. VF stands for final velocity. Since it's a velocity, it's measured in meters per second. VO is original or initial velocity, also measured in meters per second. So the reason why I included the units here is because it's super important to note that these equations, so whenever we're given a problem, the first step we want to do is draw a diagram and set our origin. And we're going to do that below. Start off with my plane. After I have my plane, I'm going to draw my runway. And then I'm going to label the distance of that runway. I see in the problem up here, it tells me 2,000 meters long. So that's talking about some distance because it has the meters there. And 2,000 meters is in reference to where I'm starting. So I'm going to give my initial starting point 0 meters. And this will be the case 99% of the time, if not 100% of the time, that our initial distance will be 0. So if our origin is set at the plane, then whatever distance we say is at that origin is going to be 0 meters because we are 0 meters away from that origin. Now we're just going to go ahead and start labeling these variables below. Again, DF is the final distance that this plane will reach, and the end of the runway is 2,000 meters, so we put 2,000 meters here. The next one is the initial distance. We look at our picture and we can see that we're starting at 0 meters. Acceleration and time, I don't see that mentioned anywhere in the problem. So we're going to go ahead and put those as question marks because we are unsure what they are at the moment. And this works out because anytime that we're solving a kinematic type problem, we need at least 4 variables. So we should always know at least 4 of these. If you're ever stuck and maybe you've only labeled 3 and you're missing the 4th one, think about where is it starting at? So that initial distance, like I said, is almost always 0. And then also, is it starting at rest or ending at rest? If it's starting at rest, then it should be an initial velocity of 0 meters per second. If it's ending at rest, so if it's coming to a stop at the end, then the final velocity should be 0 meters per second. So you got to pay attention to those keywords as well. So the next step, like I said in the slide before, is that we want final velocities in meters per second, just like we have our initial velocity here. But this one says miles per hour. So we're going to have to go ahead really quickly and convert that number into the physics units that we want. So we're going to set up a unit conversion just like we did before, 180 miles over 1 hour. Our first conversion is 1.61 kilometers over 1 mile. Then from there, we're going to do 1,000 meters over 1 kilometer. And lastly, 1 hour over 3,600 seconds. So now we're going to cancel out the units. Miles cancel out here. Kilometers cancel out here. We're just left with meters, which is what we want. And then hours cancel out here, and we're left with seconds. So we multiply our way through, and we find out that we should have a final velocity of 80.5 meters per second. This is good because we know that we're in meters per second. And also, if you're unsure if you did this step right, just Google it. So go ahead, head over to Google and just convert 180 miles per hour into meters per second to make sure that your answer is correct. So now that we have all of our initial values and they're all set into the correct units, we can go ahead and start solving for either acceleration or time. So we want to choose an equation that's only missing one of those variables. So which unknowns should we solve for first, and which equation should we use? Well, again, we can either solve for acceleration or time. So we need to look for an equation that's only missing acceleration or time. In this equation, I see acceleration and time. And in this one, I also see acceleration and time. So the only equation I can use is going to be Shaggy Cat. And just like I said over here, we have to use Shaggy Cat to solve for acceleration because the other equations both have acceleration and time. So we're not able to use those at the moment. So here's our equation. First step is always to write that equation down when solving. Next, we're going to go ahead and plug in our numbers for our variables. Final velocity was 80.5. I notice velocity is squared here, so I'm going to square this number, is equal to our initial velocity, which was 0, still going to square it, plus 2 times a. A, we don't know, so I'm going to leave as a, times df minus do. df was 2,000, and do was 0. So I just simplified this in one step and made it 2,000. Now I'm going to go ahead and do some math. 80.5 squared gives me 6,480.25 is equal to 0 plus 2a times 2,000. The 0 cancels out because it's just 0. It doesn't matter. Again, just taking it slow, I got rid of the 0 here. Now I'm going to multiply 2a times 2,000. But instead of doing that, I'm going to divide the 2,000 over. And then after I divide the 2,000 over, I'm left with 3.2401 is equal to 2a. Divide 2a over, and I get acceleration is equal to 1.62 meters per second squared. What does this mean? Well, this is just telling me that the plane was accelerating at a rate of 1.62 meters per second squared during its takeoff. So now we're going to solve for our last unknown. And if you remember, that last unknown is time. So which equation are we going to use to solve for time? Well, we have two options here. We could either use big dog or little pup because time is in both of these. It doesn't matter which one we choose. I'm going to recommend that we use little pup because this equation is just a lot easier. There's only 4 variables and there's only a little bit of multiplication, where the other equation we have 1/2, we have t squared, and it's just a little bit more complicated if we were to use big dog to solve for time. And also, big dog has 2 times in it, so we're going to have to do some manipulation to just solve for one of those times. So here's our equation below. VF equals VO plus AT. We're going to go ahead and plug in our numbers just like we did before. 80.5 for VF, 0 for VO, and then A we just solved for is 1.62, and T we don't know, so we'll leave as T. 0 just goes away, so we're left with 80.5 is equal to 1.62 T. And we get 80.5 divided by 1.62. That's going to give us a time of 49.69 seconds. And what that time is telling us is that it took the plane 49.69 seconds to take off from Midway Airport, which is pretty reasonable. And next time you guys go to Midway, not now because we're in this whole pandemic, but when it's over and it's safe to fly again, next time you guys go, time how long it takes a plane from start to finish to take off and see if we were close on this number. Now let's do a quick little recap about what we just talked about. So one step that I think is super important that you guys should always follow is drawing a picture. Always, always, always draw a picture. It's important to note though that when we draw that picture, we need to make sure that we're labeling our origin. So label an origin. And then also we are labeling any important information. After we have our picture drawn, it's super important that we list all 6 of our variables. And then after we have listed all 6 of those variables, we either need to fill out what they are, or we need to mark them as unknown. Another really important thing to remember is that if we're ever given a number that's in non-physics type units, like miles per hour, we need to make sure that we're converting that into meters per second. So convert non-physics units. After you have all your variables listed, you're just going to go ahead and solve for the 2 unknowns. And the way that we solve for those unknowns is that we need to find an equation where we're only missing one of those unknowns. And then we're just going to repeat these steps until we have no more unknowns left and we've solved for every variable. Last thing I want to mention is that we need to pay attention to keywords like at rest and how at rest means that our initial velocity is 0 or comes to a stop, meaning that our final velocity is 0. And then also, like I said before, 99% of the time, your initial distance will be 0 meters. And that's because we're setting our initial distance at that origin.